In 1933, after fleeing Nazi Germany, Einstein settled in Princeton, New Jersey. Working in solitude, he stubbornly continued the quest he had begun more than a decade earlier to unite gravity and electromagnetism. Every few years, headlines appeared proclaiming Einstein was on the verge of success, but most of his colleagues believed his quest was misguided and that his best days were already behind him.
Einstein in his later years got rather detached from the work of physics in general and stopped reading people's papers. I don't even think he knew there was such a thing as the weak nuclear force. He didn't pay attention to those things. He kept working on the same problem that he had started working on as a younger man.
When the community of theoretical physicists begin to probe the atom, Einstein very definitely gets left out of the picture. He, in some sense, chooses not to look at the physics coming from these experiments. That means that the laws of quantum mechanics play no role in his sort of further investigations. He's thought to be this doddering, sympathetic old figure who led an earlier revolution but somehow fell out of it.
It is as if a general who was a master of horse cavalry, who has achieved great things as a commander at the beginning of the First World War, would try to bring mounted cavalry into play against the barbed wire trenches and machine guns of the other side.
Albert Einstein died on April 18, 1955. And for many years, it seemed that Einstein's dream of unifying the forces in a single theory died with him.
So the quest for unification becomes a backwater of physics. By the time of Einstein's death in the 50s, almost no serious physicists are engaged in this quest for unification.
In the years since, physics split into two separate camps. One that uses general relativity to study big and heavy objects, things like stars, galaxies, and the universe as a whole. And another that uses quantum mechanics to study the tiniest of objects like atoms and particles. This has kind of been like having two families that just cannot get along and never talk to each other, living under the same roof. There just seemed to be no way to combine quantum mechanics and general relativity in a single theory that could describe the universe on all scales.
Now, in spite of this, we've made tremendous progress in understanding the universe. But there's a catch. There are strange realms of the cosmos that will never be fully understood until we find a unified theory. And nowhere is this more evident than in the depths of a black hole. A German astronomer named Karl Schwarzschild first proposed what we now call black holes in 1916. While stationed on the front lines in World War I, he solved the equations of Einstein's general relativity in a new and puzzling way. Between calculations of artillery trajectories, Schwarzschild figured out that an enormous amount of mass, like that of a very dense star, concentrated in a small area, would warp the fabric of space-time so severely that nothing, not even light, could escape its gravitational pull. For decades, physicists were skeptical that Schwarzschild's calculations were anything more than theory. But today, satellite telescopes probing deep into space are discovering regions with enormous gravitational pull that most scientists believe are black holes. Schwarzschild's theory now seems to be reality. So, here's the question. If you're trying to figure out what happens in the depths of a black hole, where an entire star is crushed to a tiny speck, do you use general relativity because the star is incredibly heavy, or quantum mechanics because it's incredibly tiny? Well, that's the problem. Since the center of a black hole is both tiny and heavy, you can't avoid using both theories at the same time. And when we try to put the two theories together in the realm of black holes, they conflict, it breaks down, they give nonsensical predictions, and the universe is not nonsensical, it's got to make sense.
Quantum mechanics works really well for small things, and general relativity works really well for stars and galaxies. But the atoms, the small things, and the galaxies, they're part of the same universe. So there has to be some description that applies to everything. So we can't have one description for atoms and one for stars.
Now, with string theory, we think we may have found a way to unite our theory of the large and our theory of the small and make sense of the universe at all scales and all places. Instead of a multitude of tiny particles, string theory proclaims that everything in the universe, all forces and all matter, is made of one single ingredient, tiny, vibrating strands of energy known as strings.
A string can wiggle in many different ways, whereas of course a point can't. And the different ways in which the string wiggles represent the different kinds of elementary particles.
It's like a violin string, and it can vibrate just like violin strings can vibrate. Each note, if you like, describes a different particle.
So it has incredible unification power. It unifies our understanding of all these different kinds of particles.
So unity of the different forces and particles is achieved because they all come from different kinds of vibrations of the same basic string.
It's a simple idea with far-reaching consequences.
What string theory does is it holds out the promise that, look, we can really understand questions that you might not even have thought were scientific questions. Questions about how the universe began, why the universe is the way it is at the most fundamental level. The idea that a scientific theory that we already have in our hands could answer the most basic questions is extremely seductive.